Morning guys. So there's a lot of confusion on the lab final about how to find your tau on the oscilloscope, so I'm going to go over it very quickly with you guys. So let's assume we have an oscilloscope screen. Mine's not to scale, but it'll give you an idea. And you have a signal coming in, and let's say it was at steady state, and then you hit the switch and it fell, and then you hit the switch again, went back up to steady state. So we'll handle both of these cases. And I'm just going to put some labels on here. So that's your max volts, and say your design was perfect according to the specifications. So this was like 9.5. And that was your Vmin right here. And we'll assume that was 4.5. For your final design, you could have picked a number between 4 and 5 and 9 and 10. So we're just going to assume they're right in the middle. So you want to find and show your GTA where tau is on your screen. So something to notice, you hit the switch right here and right here. So we're going to say that's where t is equal to 0. And then for the next state, it's going to be t is equal to 0 right there. Okay, so what you're wanting to find is where to put your cursor. Now you can't put your cursor on t equals 0, but you can kind of see where it is. But where would you put your cursor to find tau? So if you think about it, this is our equation that we went through in class, and we'll convert it to v's, but what you have is v of t equals tau is equal to v when t is equal to infinity. We'll talk about those in a little bit. That was your K1 if you solve the differential equation. And then you also have this business, and that's just v at 0, or 0 plus, minus your v at infinity. And I'm just using the shorthand here. It's the same as this. I'll make it consistent. Just erase that. And then you multiply all of that by e to the negative. Now remember, t is equal to tau, so we'll replace t with tau divided by tau. Now you could probably see where this is going. So you'll have v of infinity plus v at 0 plus minus v at infinity e to the negative 1. Now, so far for rising and falling, this is the same case. But what you're going to plug in for infinity and 0 is going to make all the difference. So I'm going to switch colors here, and we'll do falling first. So we'll do this part first. And we're trying to find out where tau is located on the screen. Okay, so let's say this is falling. And we'll say v of tau is equal to v of infinity. So infinity, when it's falling, is your lower value. So that will be 4.5. And then we'll just basically crank out the arithmetic here. So v of 0 is where you started, so that's going to be 9.5. And then you're going to subtract that from 4.5. And when you're looking on your oscilloscope, yours is not obviously going to be 9.5 and 4.5. It's going to be whatever the values that you measured, either with your voltmeter or on the oscilloscope, whatever values you see on your graph. And then we're going to multiply that by e to the negative 1. E to the negative 1 is like 3 point something something something, but you can throw that all in your calculator, which is what I'm about to do, and you should get a value. So I'm throwing this in Wolfram alpha, 4.5 plus 9. 9.5 minus 4.5. I cannot type this morning. My brain is not working quite right yet. So I get about 6.33 volts. So that's your falling state. So now let's do rising, which you can kind of do yourself, but I'll just do it. So if we have rising, you're going to have the same thing. V of tau is equal to, so now we're replacing this V of infinity right here. We're going to replace this with the steady state of the rising, which in this case is 9.5. So you can see how it's going to give you a slightly different number. So you got 9.5 and then plus. And now, if you look at your V0 plus, it's going to be your lower value, so it's going to be your 4.5. So you get 4.5 minus, and then once again, your infinity value, so where it ends up being, which is 9.5. And put that in brackets, multiplied by e to negative 1. And if you do the math on that, which I'm about to do, we'll say 9.5 plus, actually let me go a little further with this. So you'll see 9.5 here, and then you'll see a plus here, and this turns into minus 5. In the above example for falling, it was plus 5, e to negative 1. And that will be equal to minus 5 times e to the power of negative 1. So in your lab manual, it kind of approximates these numbers, but these are exact. So this is 7.66 volts. So now you know where you can go to find the falling and rising. So you're gonna, if you move your cursor on your oscope to, let's pretend that's 7.66. It's probably not to scale, but let's just say that. Then you know that this right here is going to be your tau rising. And on your oscope, if you put the second cursor at t equals 0, which is where it started climbing, which is this spot right here, then it'll tell you exactly what your tau is. And if you did the same thing for your falling case, which is really not to scale, but you can kind of see it's going to be a little bit lower. So say this is tau falling, and you found that voltage, which was 6.33. So you put your cursor on 6.33 right there, and you put your other cursor right here, then the difference right here will be your tau.